The broadcast is now starting. All attendees are in listen-only mode.
Well, good morning or good afternoon, whatever part of the country you're at. This is Chris Kolpak, Immediate Past President of APA. Today, in our continuous education series, we got a great webinar today scheduled. It's how will the fourth industrial revolution affect campus operations? As we look at the ability to harness big data within our facilities teams and making real-time decisions, we got the pleasure of having Henry Johnstone. Henry Johnstone is president of GLH Engineering in Tucson, Arizona, and has been a strong member of APA in our Rocky Mountain region for a number of years, sharing his knowledge. And we appreciate that. As always, you can get continuous education credits. You work with Billy on that. She'll send out certifications. We'll have the PowerPoint in our APA new revised webpage. So that will be there also in the next day or so in PDF format, and also the audio. And next month, we're looking at having President of ASHRAE, Daryl Boyce, speaking, and I'll go over that in more detail. So without further ado, Henry, we sure appreciate you coming and taking time out of your busy schedule to reach out and share with our members. How will the fourth industrial revolution affect campus operations? Henry, take it away.
All right. Thank you, Chris, and thank you to all the participants here for sitting in on this, listening to what I got to say. So I should start out just saying, why am I doing this? And the motivation here really is at the University of Arizona, we got a new president maybe a year or so ago, Dr. Robbie Robbins, a very dynamic and far-thinking kind of a leader. And one of his first moves was to build a new strategic plan for the university. And that came out maybe a couple, 3 months ago. Start to read this strategic plan, and sprinkled throughout it is the words fourth industrial revolution. How will the university as a whole adapt to this thing called the fourth industrial revolution? And so I just printed up here the strategic pillars. There's 4 major emphases the university's strategic plan has. One has to do with student engagement and student success. And if you look down in here in the words, there's the words fourth industrial revolution. How do we teach the students the skills and mindsets to become leaders in this impending series of changes? The next one, grand challenges. This really talks about the university's research endeavors, and how will the university pivot to be able to do research that's leading the fourth industrial revolution. Also in the strategic plan is advancing the land grant mission, and then actually sort of going global, expanding the reach of the university throughout the world. All 4 of these pillars are based on a foundation, number 5 here, which is what's called institutional excellence. And while the first 4 pillars are really academic and research focused, that one on the base, the foundation, the grade beam on which these pillars set, really talks about facilities management and campus operations, and how do we run a university that enables it to be efficient, high performing, and an enterprise on its own. So throughout the actual text, and the thing's maybe 75 pages, those set of words, fourth industrial revolution, occurs many times. As I read this thing, I said, as a consultant to the university, as someone who helps facilities management, planning, design, and construction, and kind of thinks about the future of the university, I probably ought to know a little more about what this is and what it might mean as we move forward in both planning the university and managing the university. So that's my motivation. How did I get my information? Well, I looked on the internet. The Fourth Industrial Revolution is a book written by a guy named Klaus Schwab, and this is really, I gotta say, a very readable kind of a 175-page book by a leading international engineer and economist. Mr. Schwab is an 81-year-old guy who was the originator of the World Economic Forum, which you might remember or recall is held, I think it's in Davos, Switzerland every year. Global leaders show up to this thing to talk about impending change and planning for the future and that sort of thing. Mr. Schwab, as a kind of a economist and geopolitical high-level thinker, his book is fairly philosophical in some ways. He talks about what the changes that we're currently seeing in technology and digital revolution, physical revolutions, what's going on in biology, how those really affect countries, how they affect politics, how they affect overall global economics, well, what the implications are in social and cultural change. So it's kind of a there's some deep ideas here. The other source I looked at is another German guy by the name of Heinrich von Schiele, and he's much more of a grounded kind of what does the changes in technology really mean practically if you're a government or an industry and you're trying to set yourselves up to be ready, to be prepared to compete in this new economy. What do you need to know? So this guy's a lot more grounded, maybe more down to earth kind of an approach, but nevertheless a deep thinker, and there's a lot of information. You can Google him and find out his stuff. So both of these, you'll see some of the images I have below. I've taken from these two sources. I should say both of them think a lot about the future. What do these technologies really mean? Not on necessarily on practically what are we going to end up investing in and how are we going to behave, but really what's the future of these technology changes on society and culture. And they're both fairly optimistic that, hey, this is not going to overwhelm humankind, but I think they both recognize that there is the level of changes and the velocity, the speed at which these changes are happening is something that we as people need to think about. The rise of the machines is a very real kind of a concept. All right, so I'll get out of the deep and potentially dark aspect of this thing and move into the why, what, when, how, and where. I think we just talked about the why we're doing this thing, and I think it's really just what do we need to know as engineers and administrators and managers? What do we need to know to plan for this impending change? So my first little image here is the past industrial revolutions. There's the first industrial revolution happened in the 18th century. You probably read about this in your history class. And this really had to do with the beginnings of steam and water power, moving away from cottage industries to cities, industrial places where there was a much more productivity. The second industrial revolution, starting in the 20th century, is really where electricity started to take over, mass production. The Henry Ford's assembly line is part of the second industrial revolution. And that proceeded until the advent of the personal computer, I think is beginning of the 1970s, programmable logic controllers. And now today we're really at the sort of the beginnings of the fourth industrial revolution, which really is a lot more than just simple computers. It's really the integration of changes that are happening both physically, digitally, biologically. It's kind of the mashup of a whole lot of things that are happening, all of which are happening at a fairly high rate, and all of which are integrated, where it's not just simply a computer in charge. It's a computer with new materials using biomimicry, for example. So that's kind of the setup of what industrial revolutions are. If I go to my next slide. Again, kind of the same idea here. As we're evolving, this kind of breaks down what this cyber physical systems really can mean. Unprecedented levels of data and increased speeds, just the massive amount of processing that can be done even on your laptop computer or your cell phone. Ubiquitous connectivity, so everything getting connected quickly, and the sensing and actuation, which I think on a campus you're definitely seeing this kind of behavior. The Internet of Things is really starting to form in the campus operations. I think we're at the advent of data analytics, and I think at the end of this slide, I think this is one of my suggestions for really something that we should pay attention to as engineers and managers of university systems, is really harnessing the opportunities of data analytics for improving efficiency. And then new cyber physical technologies. We'll talk a little about what those can mean to a university. The biggest parts of this, though, are over here on the right-hand side. The reason this is called a revolution, this is not just a continuation of what we've seen in the 70s, has to do with the velocity of change, how quickly things are changing, the breadths of those change, and the overall impact they're making. Often hard to determine, sort of a priori, what impacts we're going to see from technology changes. So let's go back to the first industrial revolution. This is the one that happened in the 1800s. And we thought, if you historians, I guess you'd say, think of that as sort of diffusion. It took 40 years for that industrial revolution, those ideas, those technologies, those ways of producing things to spread through Europe, starting in the 1840s to the 1880s. It's a very slow kind of process of adoption. Now compare that to what we're seeing now, throughout the world here. The rate of change of new technologies is increasing. So here's where the car was introduced in the early 1900s. Fairly steep initial kind of absorption, a period where stability, and then a fairly gradual increase of the number of cars, the number of people that are actively buying cars. Another example might be air conditioning. Here's what air conditioning looked like. The absorption of air conditioning technology was a fairly slow and linear process, that expand over 40, 50, 60 years from its 1950s, when it really became something that people could afford. But now compare that to what we see with the tablet, for example, an almost vertical line on this scale here, very rapid increase of absorption. Here's the smartphone, almost ubiquitous now. Everybody's got a smartphone, and it happened within the last, say, 10 years. Remarkably quick absorption. So that's what we think of as velocity of change. Here's another example, more connected to the digital world. The mainframe computer in the 1950s, fairly slow, gradual rate of adoption, and kind of leveling off here in the 1990s. Compare that to something over here, artificial intelligence, for example, a much more rapid rise in how that technology is applied across the world. So with this increased velocity, we start to see things that are really called disruptive technologies. Just a few examples here. Certainly the shared economy that you see in Uber and Airbnb, the ability to do commerce over the internet and have almost no interpersonal relationships in doing commerce. The iPhone Siri, which really is artificial intelligence, the beginning of artificial intelligence. And all of this has happened very, very quickly compared to earlier revolutions. Here's another little picture that kind of gives you that idea of acceleration. The printing press, one of the first major things you'd say was a revolution in the way we think and do in the 1400s. It took 350 years to get to the steam engine, and then 200 years to get man on the moon. But then suddenly we're seeing all kinds of technologies that have rapidly accelerated since the 1950s. So acceleration, kind of an exponential increase. Again, it's similar to the last graph I showed. This is the number of installed sensors, and that's 1T represents a trillion. And so you can really see here the kind of the rate of change where mainframe large computing, the first wave of this revolution, occurs on a fairly gradual slope. The third wave, where we are now, this ubiquitous sensing idea, is really happening much more rapidly now. Another graph kind of showing the same thing, the Internet of Things. This is the number of devices connected together connectivity. And so same kind of time scale here. We start with 1 million devices back in the early 60s, and now we're in the billions. And you can see every year it's kind of like there's more and more stuff being added. Here's the refrigerators and kind of home appliances. Here's the utility grids being added. Here's the electric toothbrush being added. I got to admit I'm behind the times on having an internet connected toothbrush, but apparently there is such a thing. Traffic signals, thermostats, just about anything you can think of that has some reason to be automated or benefits our operation is getting connected here. And I think we see that, definitely see that in university facilities, campus facilities. So this is one of the graphs from Mr. Von Schell. He visualizes there to be 17 major, he calls them pillars as well, major pillars of this revolution, from smart automation, artificial intelligence, bioinformatics and nanotechnology. Here's the Internet of Things, blockchain, autonomous. So there's all of these individual advancements being made, opportunities to advance that are out there now, all sort of evolving at their own rate. Now, look down at the bottom of this graph and you see sort of linear innovation from, he starts at 1784 to 1969. Things are happening fairly monotonically and at a constant slope. Whereas in about 1970, when we get to the Industry 3.0, that's sort of the advent of the personal computer, the pace starts to pick up. And now, rather than linear innovation, we're really seeing this exponential innovation. So just remember the 17 individual things that are happening all at once. And this graph gives you an idea of how each one of those technologies or concepts can change over time. So if you look at the bottom here, these sort of egg-shaped bubbles, this gives you the idea of you get a new idea. First, you go through a pilot process, and maybe there's some early adopters, but in reality, it's just testing the concept, an initial rollout. So you might think of this, the pilot. If you thought about cell phones, for example, that's the bricks we used to lunk around in our cars, back in the 1980s. Not a very practical way, but we were able to say, this actually does work. This is something that we can adapt to. Initial rollout, maybe that was the flip phone idea. Damn it, where it worked, but it was kind of clunky and ineffective, and would only allow you to do voice kinds of things. The next generation here, maybe you think about that as the BlackBerry, where we really started to realize you could move data around on a cell phone, and so there was a wide range of opportunities at that time, different technologies, different vendors, different ways of doing it, and we as people really began to appreciate it and make use of it. It became an efficient thing to do. So if you look on this graph at the performance curve, this line here, it was during that time that we're really accelerating the number of cell phones that people have. Now, finally, you get into the final bubble here, can't be successful without it, and that's clearly where we are now. You got to have your iPhone or your whatever, Android, because so much relies on having that. So that's one individual example, one of these pillars. What we're really seeing here with this industrial revolution is the combinations, the permutations and combinations of there being 17 different things, or at least 17, probably more, that you could, define, all happening at their own rate, all going through an evolution, something like this. So that kind of gives you the idea at the top here. From inception, an idea goes through a number of periods. So they talk about the inflection of attitude and the peak of hype, attitude plateaus. Another graph here I have is called the hype cycle for the Internet of Things. So it first comes out, something comes out, it looks like a great idea, everybody latches onto it, invests in it, and there's a lot of buzz about it. But in reality, it doesn't really translate into something that works particularly well right away. And so you come to this kind of peak of inflated expectation period, followed by the trough of disillusionment. It sounds pretty bleak, but that's ultimately, that's how these individual ideas, technologies, concepts mature. And then finally you get to the slope of enlightenment and ultimately the plateau of productivity. So ultimately every one of these things is going through its own little life cycle, and at any given time there's a lot of different moving parts to what's a good idea. Here's someone's projection of the good ideas. Again, I'm really just trying to reinforce awfully hard from where we are today to project what the things that are really going to be successful are, given all the dynamics here. So you can see on this graph the idea that we're now at 2020 kind of in the demonstration phase of autonomous vehicles. 5-7 years from now, we're likely to be in the commercial phase. At least from my perspective, that seems kind of reasonable. Same sort of thing with 5G. We're just in the beginning of 5G. Some of these others, I really have no idea, when foam batteries are going to come around or fusion reactors. But all of these are opportunities that rely on individual pillars, individual concepts or technologies that are developing at their own rate. Okay, so I just want to give you an example to kind of demonstrate the difference between the way things were and the way things are. Just kind of reinforce the idea that we're in a revolution where things are quantitatively and qualitatively different, moving at different rates than they used to. Okay, so I go back to this little graph that kind of shows the accelerating rate of change. There's Man on the Moon, which must have been 1969. 1971, I was 17 years old, and I had an active mind. I was really interested in new ideas, and one of the ideas, so I read scientific, popular science. That was my main source of information at the time. One of the ideas I was totally engrossed with was the flying car. This is an image of the Mazur flying car, a Ford Pinto bolted on to a Cessna Skymaster. And the idea here, which was really kind of a great idea, was to take a very inexpensive, lightweight car that's already been developed and is manufacturing, and made it with an airplane that was also in active manufacturing. The airplane, the Skymaster, was actually kind of a push-pull operation where it had two propellers. It was used in Vietnam anyway as a reconnaissance plane. Could fly at really low altitudes and really slow. But you can kind of see why they said, hey, we could use half of that airplane, made it up to our Ford Pinto, and we'd have a flying car. My buddy had a Pinto, and we used to sit in that in his driveway before we got a driver's license and imagine the day we'd bolt an airplane to it. So this was actually at the time, an innovative idea, made it to popular science. And these fellas actually built a couple. I think they built 4 of these things and were able to test it. It had 2 flights. The first flight with a test pilot, the strut that bolts the wing to the Pinto failed, and the wing kind of became loose. The test pilot carefully landed the thing in a bean field outside of the airport in Van Nuys, and then miraculously drove it back over the road to the airport with its lame wing. That got subsequently welded back on, and the next time it flew was the chief engineer and the owner of the company Henry Smolinski and Howard Blake. They figured they didn't need the test pilot. They took it up, and that time the weld broke, but unfortunately they turned into the wing that fell off, sending the whole apparatus plunging down into the ground, ended in a fiery crash, and unfortunately took their lives. That was kind of the end of that great innovative idea. What I want to get across, though, is that was really mating two existing technologies that were all both sort of fully matured, taking two ideas, combining them to make a new idea, a linear process. So now you fast forward to today, and if you look on the internet at flying cars, you come up with a lot of stuff. This one I find particularly appealing. This is a human passenger drone. Actually, you can get two people in this thing. This image is showing it flying as a remote-controlled passenger drone. So the basic concept here is you call up, say, I need somebody to pick me up. The drone comes on its own, flies on its own, lands, picks you up, takes off, takes you to your destination. Now, I suppose you could probably take over the controls if you wanted to and fly it, or it could be some kind of an autonomous vehicle at some point. But in the original concept, it's really just a drone. Some interesting facts about this, from a material standpoint, made out of extremely lightweight, modern technology, modern 3D additive printing, new ways of construction go into this thing to make it as light and as efficient as it is. It doesn't run on gasoline. This is a lithium ion powered 16 individual propellers, a completely different way of doing a vertical takeoff kind of a vehicle here. So it's adopted many different developing technologies were incorporated into the design and manufacture of this device. Now, the reason for why does it make sense is pretty obvious. Here's an image of something that's extremely inefficient that humans do all across the world, which is sit in their vehicles for hours at a time, just trying to get from home to work and back again, or home to the store and back again. Very inefficient use of human resources, as well as being inefficient use of, steel and aluminum and plastic, and an inefficient use of fossil fuels to move it around. So there's a great opportunity to say, if we could fix this, we could really make ourselves a lot more productive. So you take the idea of here's a drone, which you might say this is a disruptive technology, and you say, what if we combined that with something that happens in biology? This is an image of bats leaving their normal habitat under a bridge. Every evening this happens. The bats go off to find mosquitoes to eat. They're chasing insects. They all go at once. In this case, there's thousands of them leaving the bridge. In this case, there's a cave in Mexico where there's literally millions of bats that all at the same time leave the bridge and somehow miraculously are able to coordinate their flight so that they don't run into each other. They go to where they want to go, they turn around, they come back, and they all end up safe back at home here. So here's my idea, and this is my brief moment of pretending I'm Elon Musk and telling you how the future is going to be, is we take these little drones and we use biomimicry to figure out what it is that bats do, which I think fundamentally is sensing on the bat itself has very good echolocation, can figure out where the bats are adjacent to it are and steer around them. Use the same basic idea with these little drones and incorporate that into everybody wants to go to work, and we're going to be able to coordinate ourselves without a lot of brain power, but a lot of remote sensing using basically biomimicry. So this is, again, just an idea of how you could use physical, digital, and biological technologies together in some way to greatly improve, the human situation. Now, it's probably true that this is a bad idea in a lot of different ways, and I'm not representing you buy stock in my company. Okay, so while neither one of our resources there Heinrich or Klaus really talked about facilities management and how the fourth industrial revolution affects that. They do talk about the overall effects on business, and I think these are what's most relevant to FM. The highest one here, customer expectations. So the people we serve are now becoming endeared with this idea of fourth industrial revolution, and their expectation is that we are equally endeared and on top of this thing. Product enhancements, that's new materials and methods. Collaborative innovation, that's a big one, and I think we're seeing more and more of that, certainly in the design world, but more and more with our clients in facilities management. And then different organizational forms. Because of these technologies, we can structure ourselves differently and more efficiently and more effectively. So keep in mind these major things to pay attention to if you're looking to answer the question of how does the fourth industrial revolution impact my world. This is a graph. So I'm in the architect, engineer, construction business. I'm a consulting mechanical engineer. We design buildings for clients, including universities. This is a kind of a graphic of the various opportunities that are available in our industry to improve our performance and in response to the fourth industrial revolution. All of these, you'd say, were results of this fourth industrial revolution. What I find remarkable when I looked at this graph was the number of these that we, as a 60-person A&E firm, have invested in, adopted, and are just basically fully utilizing in the last 7 years. We've picked up prefabrication. We're doing projects that involve modular construction, prefab. We're using augmented reality. We're heavily using the cloud and real-time collaboration tools to communicate with people all around the world in design projects. 3D scanning, heavy use of that. Big data is, I think, a fundamental shift, probably more so in operations than in design, but there's a lot available there, and I'll talk about that in a minute. And then finally, building information modeling, which we've almost completely evolved to from the days of two-dimensional hand drafting to AutoCAD, and now everything really is being done in our world in 3 dimensions. All of these represent large investments in not only in buying the software, the platform, the pieces and the parts, but probably more so in teaching ourselves how to make use of them. So just a couple of examples here. Utility in the realm of modular construction, the place we've most used this is in utility plants. These are sort of what we used to call package plants, but we're seeing this more and more frequently, opportunities to construct an entire chiller, heater, boiler, cogen plant off-site in a factory under factory-controlled conditions, get it all put together, welded together, wired together, controls installed, tested, compared against the energy model, and then unbolted and shipped to site and put back together. I got to say, as a mechanical engineer 10 years ago, I poo-pooed this idea. You know, this will never happen. This is a real cheesy way to build stuff. We can do a lot better if we stick build it. You know, we can build a plant on site that's a lot more efficient than one of these guys, has better maintenance access, easier to work on, that sort of thing. But the modular chiller plant industry responded to those concerns. And really, I got to say, in many cases, not all cases, many cases, the product you get at the cost you get from a packaged chiller plant vendor is every bit as good as what we could do stick building it on site, meets the same kind of schedule requirements, may not be a whole lot cheaper, but competitive. So certainly in a very complicated kind of build environment, prefabricated off-site modular makes sense. Another example is laboratory buildings. We're actually involved in a couple of modular labs, wet labs, where we're building the entire infrastructure in shipping container sized boxes, not shipping containers, but sizing boxes that'll go over the road or on a sea container. And which are fully populated with the utility racks, the drywall, the cabinetry, the fume hoods. Everything's basically built in the factory. And that, again, at some scale doesn't make sense. If you're on a university campus, you're probably not going to build a 150,000 square foot lab building this way. But if you're looking at a 20,000 square foot lab, it's becoming cost effective at this point to do it this way. Now there's some change, there's some compromises that got to be made. It's going to have to fit within a shipping container, so that sets ceiling heights and column widths. But in reality, that's a workable kind of a deal. Here's an image of the inside of a finished lab. You can kind of see, if you look, that's the double column, so that must be one of the box splits. But ultimately, comes out as useful, as functional as a built-in-place lab. In this case, the real benefit of this wasn't so much it was cheaper to build, it was just a lot quicker to get built, because you could be building the foundation at the same time the modules would be fabricated off-site. So wet utility labs, another thing where it's almost here, and I think from that standpoint, from facilities, you need to be looking at that. Certainly office buildings, another opportunity, and you get an idea here of what a modular office. There's residence halls. This is taking hold across the industry. Another example of what we're starting to see here, autonomous construction. This is the largest 3D printed concrete bridge. I think it's in Japan. When you go to a 3D printer that's able to push out concrete, you can come up with some incredibly innovative, interesting ways of building a structure that we simply can't do in a poured in place or precast environment. So here you got to get the idea of building the structure as a honeycomb, building the structure with less material but every bit the same amount of strength. Here's another 3D printed bridge, or a 3D printed building. This is the Corps of Engineers, and their mission here was to be able to build barracks in a very remote site using local materials without having to bring a lot of stuff in with helicopters or trucks. So the idea here was build a printer system that's large enough to build an entire barracks on site. This, I think, at the point this photograph was taken, was day 3 of the build. Now, that was kind of an ugly looking thing. That's early days. This is a 3D printed truss structure that gives you the idea of, hey, these things can be kind of elegant, lightweight. It doesn't have to be the toothpaste tube of concrete idea that we saw in the last image. Haven't seen a lot of this kind of complexity yet, but I think this is within 5 years, we're going to see more and more of this robotic fabrication of 3D printed materials. Okay, so the rise in machines, a little graphic from Reuters showing an estimate of where we're going to see the investment in machines here. There's commercial in the purple. All of this going up at an exponential rate. The title, Rise of the Machines, I couldn't stop myself from pasting this image in there. Kind of looks like War of the Worlds. These are robotic, or actually I think these are remote controlled demolition machines where there's a human is not needed to be in the workspace itself, but you could almost imagine this kind of thing being programmed and having very little human interaction. Now I want to talk about BIM, Building Information Modeling, because I think there's something here of importance to facility managers in the campus environment. As I said before, we as architects and engineers were really compelled to invest in this. Probably 10 years ago is when our initial heavy investment, and sure, the software cost a lot of money, but way more expensive was the training it took to get a staff that could adapt, could shift from being oriented to 2 dimensions, drawing lines on a page, to really visualizing, designing, detailing, cost estimating in 3 dimensions. Substantial amount of investment to get there. Initially, that investment was not because we imagined we were improving our productivity. interestingly, that was really driven by customer expectation. This technology is out there. Our competitors are using it. We've got to be, if not the bleeding edge, the leading edge of adopting this technology and getting proficient at it, or we face the prospect of not being competitive, losing work, not being able to keep up with our colleagues here. So similar to what I think FM faces here, a big driver in our decision to invest in building information technology was really customer expectations. And it's not necessarily the customer as the end user or the owner. Increasingly, our customer is the construction industry here. We're seeing more and more sort of design, build, and CMAR projects where in one way or another, we're really one of the multiple subcontractors that the constructor has. And this has happened quite rapidly. The adaptation of building information modeling in the construction field. So if you're doing anything larger than say a 10,000 square foot or 20,000 square foot building, and you've got a construction manager at risk or a design builder in play, I'm going to guess it's going to be a building information modeling system, and there's going to be a handover from what the architect engineer is doing to what the subcontractors are doing, how they're actually putting together their fabrication drawings, their overall coordination, increasingly complex handoff from the design phase to the construction phase, and increasingly important that the details right at that interface, the conflicts that are in the model are resolved before the contractor will take it over. So this is just a kind of simple example. I'm sure you've seen others maybe more complicated than this. This is a chemistry lab that we're involved in, which is really just showing the layers for building structure with the layers for ductwork and some of the piping, some of the larger piping there. And from our perspective as designers, from our perspective as designers, yeah, this is how we figure out how to lay out systems where they don't interact with each other. So we've got the ductwork in a place that's not going to run into a beam, or we've got the ductwork and the piping figured out, or the ductwork and the electricity. So we're using this just to get everything in the right spot, a physical coordination kind of an effort. And that's really what we examine the most carefully in clash detection. What the real opportunity, though, for facility managers is to use this model as kind of the basis for where all of their instrument points are, all their sensors are, all their maintainable devices. So embedded in what we provide is information on what the individual device, what a mixing box is, what kind of actuator does it have, what are the filters that go in that air handler on the roof, you know, specifically, what are the light fixtures? So all of the information that goes into the building is available inside that model. And if the facilities managers chose to do so, they would have complete access to that from a preventative maintenance, maybe even a reactive maintenance standpoint, and from the standpoint of analytics, knowing how the sensors are working, what the temperatures are, what the lighting levels are, is all available in there. What I think I've seen, at least to date, is a real reluctance, this idea that we're handing over the model to facilities management. There's not usually, at most universities, there's nobody at the facilities level that says, give me the model, I want to start playing with it. A lot of resistance because they're at the same phase of this thing that we were 10 years ago. It's pretty hard to learn how to use it. It takes a big investment to learn how to actually become competent in it. And when you're from a facility standpoint, if you're looking at this thing, you're saying, the return on investment, the amount of value I get out of knowing what kind of filters I have in that air handler and being able to call that up from my office and order new ones versus sending my guy out with a clipboard to go take the data down. that ROI is difficult to justify. Takes a long time, to say, if we were to implement building information modeling in our operation, we're going to see an immediate reaction. However, I think what's going on here, your customer expectation is mounting, and there's going to be more and more reasons why you as facility managers are going to need to adopt this and really start to use building models in your daily life. Okay, I'm going to advance the slide. There we go. So we get to, this is kind of the gap between what technology can provide and what actually makes sense from a business standpoint. And facilities management is ultimately a fairly conservative endeavor. And so, sure enough, it takes a while. Go back to my next slide. So let's just talk about customer expectation. This is an area where I think facilities managers are really challenged, and that's in the area of sustainability, the greenhouse gas commitment, the efficiency of their operation, energy use intensity. These are things that I think you're getting challenged by, not just upper administration who signed the greenhouse gas commitment, but I think the staff and the students are increasingly really pushing the operation towards, we've got to demonstrate that we're being environmentally responsive and we're meeting our commitments here. But that's subject, typically that's subject to the constraint of whatever we do as facilities managers needs to have a return on investment, has to be financially prudent, a good investment. So here's one example. Now this has got 4 generations of heating systems. This is not really the 4th industrial revolution. This is the 4th generation of heating systems here. And I just want to point out that most of the universities, most of the large state institutions and the universities that were, have been around for a while, are on the 2nd or 3rd generation of this thing. So what we're trying to represent in this graph is that over time, heating system temperatures have dropped. Used to be superheated, high temperature steam, then it became saturated steam distribution systems. More recently, what we're seeing are hot water systems that run under the boiling point. And as that has happened, the overall efficiency of the utility operation has increased as that temperature has dropped and the temperature differentials ultimately have increased. And so now many universities are kind of faced with having an older generation steam distribution system, yet being challenged by the president's greenhouse gas commitment to make a major change in their total amount of emissions. There's ways to do it if you simply swap to the newer low temperature hot water distribution and use two-way district heating, heat pumps. There's a lot of cool ways that you can do this. Biomass, be able to demonstrate made drastic improvements in our greenhouse gas commitment. However, it takes a major investment to do that. So I think this is a real challenge, to meet these edicts from on high and from below. We want to be more efficient. Tough to do that unless you come up with a lot of money. Another example is in the energy use intensity. So this is really the building performance. This is a graph at the University of Arizona of all the buildings on campus there, kind of chronologically organized from the 1890s to now, and colored by different building types. The reds are lab buildings, the greens are academics, the yellows are residence halls. And I blow up a little example here. And if you just compare the McClellan Hall, that's a green on the left-hand side, to ENR2, both almost the same size building, both classroom, office, and light computer labs, very similar buildings. And you can see, hey, look at that. A building built recently consumes about half the amount of energy on an annual basis than its colleague that was built 20 years ago. So it's certainly possible to improve drastic improvements in buildings, but that's going to be the difference between a new building and an old building. What you really are faced with is a whole lot of old buildings here. You're burdened by this giant fleet of aging buildings, which are consuming vast amount of energy. And this, I think, is the big challenge that fourth industrial revolution, some of these concepts can help you with. Big data, and that's really getting into this analytics kind of thing. Many campuses now have fairly sophisticated building automation systems. There's a lot of data available, but there's no logical way to convert that data into actionable information. You got massive amounts of data spitting out of the computer, being stored in an archive somewhere, but there's no simple way to say, what am I going to do with that data? A couple of examples of, sort of over time, the evolution of some of these databases. GIS, Geographic Information Systems. This is a GIS at the University of Wyoming we're involved in, put in place maybe 10, 15 years ago, but over time, this has really become a more and more useful tool. One of the things that can be done now is basically using a cell phone to input data into this large system, which makes it very practical to update the information that's in this thing, making it much more useful for modeling and analytics later. And I think of this as a mechanical engineer in kind of energy terms, but GIS has uses across campus. Here's something from the public safety folks who look at GIS as being an advantage to them. I'm sorry. So I just wanted to show you, I know this is another technology we're using here that is kind of interesting. This is a three-dimensional camera approach that allows us to go into a tunnel and document existing conditions in a completely three-dimensional interactive kind of manner. So here we are back in our office at our desk saying, I wonder what kind of pipe we got in that stretch of that tunnel, and we can call it up. And I think that could be very useful to many universities. This little program we're using can also be converted into a point cloud and then a BIM model and then actually used for design. So it's a very handy kind of a thing that was only really available at a reasonable cost 5 years ago. Now I want to get into this energy information management system. This is where I think there's a great opportunity now to handle the big data. Information systems, there's the actual system itself, which really, again, many universities already have the inputs here. They already got the points out in the field. They've got the communication back to a central point, a server, a historian. What they lack is the ability to analyze this thing and display it in terms that a human can really make good decisions on. And so that's really what an energy information system is. On top of that, there's some other even slicker kinds of features that can be added to that. Software that automates the process of finding faults, comparing today's data to yesterday's data, looking for points that went 0 or infinite or negative, and identifying what the fundamental issues are, flagging the issues so that they can be fixed. And then automated systems that kind of self-taught systems, almost artificial intelligence, that allow adjustments to be made to optimize performance. Or if it's not completely automated, it's semi-automatic, where it's prompting the operator or the user, here's things you might think about doing to improve operation based on yesterday's performance. And ultimately, going back to that graph I showed of all the university's buildings, the assets you've got, and how, generally speaking, poor their energy performance is going to be, is the idea of monitoring-based commissioning. So here's a little graphic that shows maybe we're already collecting the data. The next step is to use the analytics to identify it, prioritize it, figure out what the opportunities are, make change, implement change, and then verify that it's working, and then do a kind of a cyclical process here. This is really the solution to building energy use on large campuses that have been around in a while. Some kind of monitoring-based, real-time understanding of what the energy uses are and what it takes to get them recommissioned. Lots of opportunities here. This is from an NREL study, really looking at the kind of the difference between, hey, we've already got the ability to look at graphs and charts of what energy usage is in buildings. What's vastly more important is the ability to compare real-time data, what it's doing right now, to what it could be doing, what it should be doing, what it did last year at this time, and running the kind of the analytics. So the idea of a dashboard that's comparing performance to history and to the opportunity. Another graphic of a process. This is one of several large energy management information system vendors, but basically collecting the data, benchmarking, analyzing, planning, acting, measuring, and going back and doing the process again. Now, the one thing I got to say here, you can't be lulled into the we'll buy the software and this will work on its own. That act box there is absolutely critical. You've really got to have you really have to have people, humans, energy, effort, intelligence put into that part. The rest of this enables, a really good process, efficient process. But the idea that you really have to have people empowered to make change is absolutely critical to this thing. And that kind of goes back to Mr. Schwab's idea that one of the big changes in the fourth industrial revolution is really generating organizational change. And I think as we've talked about this idea with operations folks in the past, current shops structures don't really encourage someone to step up and say, I'm going to fix this building. Even though we have the tools to evaluate it, the metrics to be able to say this could happen, the metrics to say, hey, we'll incentivize you if you can make this building work better, the structures just aren't there. And so I think that's something to really think about. Are there ways to restructure the operation where this kind of behavior is really encouraged? So now we go to the kind of the ROI question. Well, does any of this make any sense from an economic standpoint? Does investing in an energy management information system and investing in the people to make it work, is that going to have a payback? And it's kind of early days for this, but here's an example of a study done by U.S. Department of Energy, Berkeley Lab, in which they took a sample size, not a huge sample size, I think there might have been 30 buildings in there that had these kinds of systems, evaluated what they cost, what the annual labor cost was, and what the savings over the ensuing 5 years were, or 3 years, I'm sorry, ensuing 3 years. And basically this graph here is demonstrating when they implemented this thing and tracked it over the next 3 years, on average, they got a 22% reduction in energy. And that's the kind of reduction in energy that generates an ROI when you're investing in this sort of software and again, the people that really make it work. Okay, here we are. So ultimately, when I look at this thing is a challenge we've got, and I think in facilities management, we've got this as much as any other industry, maybe more so because it's a fairly conservative, reactive kind of a operation, is technology is outstripping our ability to adapt, and we just have to kind of live with that as, okay, that's a reality. We got to face up to that, but we've got to start preparing for technological change. And I guess my basic premise here is the way to do that is through beginning to do the analytics that allow you to convert big data into actionable information that allows you to become more efficient. And with that, I'm done.
Well, Henry, that was outstanding, and you sure gave our members a lot to think about. We got a lot of questions that have come in, and we're going to run short of time, but we got one here from Tom Shaween. Are you familiar with BIM to FM, transitioning to operations, a method for BIM data to be mined into IWM systems for operations and maintenance? Are you familiar with any of that there, Henry?
I gotta say I'm not, but that sounds like exactly the kind of thing where you're not encumbered by the entire design and construction model. You're able to pick off the most effective parts of the BIM model for your uses. So that sounds like a very important development.
Well, Henry, outstanding presentation. We got questions that are coming in about the monitoring-based commissioning, and especially with the older buildings and the ROI. We have questions that have come in about fault detection and diagnostics and how we can use that to drive down our energy costs. The big buildings and the building roadmaps to address those challenges. And then how about handing off the newer buildings, all these high-tech buildings now for our facility staff. In some cases, our staff have been in these buildings for 30 years, and we're asking them to do new items. But unfortunately, we're going to run out of time. And so we will go ahead and be addressing these in future webinars. And so again, Henry, any final thoughts before we wrap up today's presentation?
Well, I think it boils down to people and their commitment to improve things. And if you've got the right staff that wants to make use of these developing opportunities, I would suggest you encourage them as best you could.
Well, Henry, we appreciate it very much. Our buildings are going through, we're living through a disruptive stage with the big data, and to be able to harness that, the Internet of Things, and to take Henry's strategic and competitiveness to make sure that our facilities departments are staying on top of the curve. That's what APA's webinar series is about giving back to our members, continuous learning, and boy, are we seeing there's some great opportunities for that. So Henry, we appreciate you and GLHN sharing your knowledge. We appreciate very much all your support of RMA and also APA as a whole at the Institute and other opportunities. And we appreciate we had everybody who registered stayed online for the entire presentation. And so again, this is APA's way to give back to our members in a very effective manner. Billy, thank you for getting these coordinated always. With that said, we'll have this posted on our webpage in the very near future. July 25th will be our next webinar. Daryl Boyce, president of ASHRAE, just came back from there, had a great opportunity to talk with their executive team and how APA and ASHRAE can continue partnering on technical knowledge, webinars, and other items. Daryl will be talking about building for people and performance, achieving operational excellence. We're coordinating with Daryl right now. We believe his schedule will allow it, and we'll be confirming that soon. So again, thank you, everybody. And Henry, thank you very much for sharing your knowledge. Have a great week, everybody. Take care. Bye.
Thank you.